Hello, you're welcome. All right, so we continue from where we stop. So here we're going to be looking at the energy that is stored by a capacitor. A capacitor stores charge and at the same time it stores energy. Okay, the charge of a capacitor stored by a capacitor can actually enable it to do work. So how can we be able to evaluate the energy um, of a capacitor? Okay, due to the charge that it stores. All right. So now, for us to do that, it's just gonna be easy. Remember, energy is actually the energy of a capacitor is what, okay, leads to work. Energy is equivalent to work. It's also equal to work because energy is the ability to do work. So a capacitor can do work because it stores energy in an electric field. So how do we actually evaluate that energy? Now we know very well that when we treat electric potential, we see that the electric potential V is giving us work, okay, done per unit charge. So invariably now work is equal to charge multiplied by. So that way, and we know that energy is also equal to work. All right. So now, so this capacitor stores energy because it has charge, and of course there's a voltage supplied to it, so it's charge times voltage. But in the case of a capacitor, all right, the charge is being stored in the plate of the capacitor, and a capacitor has two plates. All right, so of course a capacitor have two plates, so the average charge stored by the two plates is going to be equal to the total charge divided by 2, because the capacitor have two plates. So the average charge stored by each plate is going to be total charge divided by 2. All right. Then of course multiply by V. So invariably we can say that energy of a capacitor is giving us half the charge it stores multiplied by the voltage supplied to it. All right. So that's the energy of a capacitor. And of course we know that from the formula. Okay, I call this formula 1. Okay. Now this is one formula of evaluating the energy of a capacitor. We also know that charge is given as CV. Okay, so invariably I can also express energy of a capacitor to be equal to half Q, which is CV, times V, which of course will give me CV square. All right, so this is another way of expressing the energy of a capacitor. This is another way of expressing the energy of a capacitor. We also know that voltage from this relationship is equal to charge divided by the capacitance. All right. So energy can also be expressed as half, okay, charge multiplied by V, which is Q all over C. Q times Q will give me Q squared. That's going to be Q squared divided by C. So these are three ways of expressing the energy of a capacitor. So depending on what is given in that question, then definitely uh, what is given in the question, the parameters given, you can use either equation 1, equation 2, or equation 3. All right. Okay, let's look at some typical example. Let's look at a network. Okay, let's look at a network. A network of capacitors. Okay, pardon me. Okay, point A, point B. Okay, so let's say everything is 2 microfarad, 2 microfarad, 2 microfarad, and 2 microfarad. So let's say the voltage supplies is supply between point A The voltage between point A and point B is 12 volts. And I'll be asked to evaluate first the total charge stored by all this capacitor, the total charge that is stored. So for me to get the total charge stored by the capacitor, please pardon me, the total charge stored by the capacitor, I have to get the total capacitance C total, then multiply by the voltage. So how do I get the total capacitance? You know very well that for me to resolve these capacitors, okay, I have two branch here. This branch and these are these two capacitors, 2 microfarad, 2 microfarad, are in parallel, okay, because of course they are in two different branches. Now when I resolve it now, I'm going to have, okay, I will end up having please pardon me, I'll end up having the circuits this way. Of course, resolving these two microfarad and 2 microfarad in parallel, I have to add it. That will give me 4 microfarad. So this 4 microfarad, okay. Then there's 2 microfarad here. That's 2 microfarad here. And of course, this is point A, my point A, and my point B. So to resolve the total now, both these 2 microfarad, 4 microfarad, and 2 microfarad, they are in series. Okay, remember what I told you, it's about their connection, it's not about how they are arranged, because it is just one straight wire, okay, one part, there's no branch all the way from 2 microfarad, 4 microfarad, 2 microfarad. That's a series connection. So invariably now the total capacitance now is going to be the sum of all of it. That's 2 plus 4 plus 2, which actually gives 8 microfarad. So 8 microfarad is the total capacitance. So that way now I can get my total charge. That's going to be 8, then multiply by the voltage 12, right? So 8 times 12, that gives me 96 coulomb. Now the next question is evaluate the energy. The energy of the capacitor, as we already know, is half QV. Okay, so that's going to be half times Q, which is 96, then times V, which is 12. So that's 6 times 96. Half of 12 is 6. So I have 6 times 96. So that's going to be 567. So energy is 5 watts, 576 joule. Okay, so that's it. All right, so we'll look at more question in the next video. See you in the next video. Thank you.